you. All right, well, I've been really busy since last time we met and got some things to show you. So let's dive right in. I created a whole Julia package for the class, and I want to just introduce that to you because I'm going to be using it extensively moving forward. It should give you a really a nice way to get your hands on these objects and play around with them and learn them. So let me go ahead and share my screen and I'll walk you through kind of where we're at with that. Okay, so let me close all these here. All right, so we've got, oops. You guys see my screen okay?
Yes.
Idea.
Okay, great. All right, so what I've done is I created a repository called coreformiga.jl, and the I'll post the link today after class. It's related to where I've got the other stuff, although this is a new repository. And I did it for real this time in that I built something. Okay, so this I did for real, meaning that it's a standalone Julia package. It's its own environment, so that when you download it and you install it, you activate it, it should download every dependency that you need, so you don't have to worry about that. I saw Eric's comment, and so I fixed that. There's also some I deployed documentation automatically every time I push. So if you go in, and they're not done, it's not done yet, but I'm going to go ahead and like in the next day or two and fill out every method so that you can see how to use it. And then here is the basic instructions on how to get the package going on your machine. You just clone it. You change into that directory, run Julia, and then you type activate period, and that will set the Julia environment to the Coreform-IGA environment. And so all of the dependencies will be available. You import Coreform-IGA, and then away you go. So what I wanted to do today was just set up and run a single problem so that you could kind of see how this works. And then we'll dive into some of the theory if we've got some time. So I set up a little problem here and that I wanted to do with you. So you can kind of see how it works. Okay, so if I go to Coreform, can you guys see my terminal?
Yep.
Okay, so I'm in Coreform-IGA and I hit Julia, and then so now I'm in the Julia environment. And so let's go ahead and run the following problem just for fun here. Let me draw a schematic of what this is. All right, okay, good. All right, so let's start off with a problem that looks like this. So there's our little axial rod. We're going to apply a traction to it. We're going to set the constraint U0 to be 0. And let's go ahead and for the beginning, let's immerse this guy in a domain that has one boundary point that's the same, but then goes off longer. So we'll test how well we can handle the traction at an interior point, and then we'll go ahead and slide the red part to the left and take a look at that. We can explore things like quadrature and all that kind of stuff. So this is a standard setting. The displacement field for this guy is going to be U0 plus H L times X over EA, because there's no body force in here. So that's 0. So it's just going to be a linear function. So the displacement field should just look like a linear. So it's a nice setting. Let's just set this term here to 1, just for simplicity, and just see if we can, how well we can reproduce this linear response. Okay. Any questions so far on this, on what I'm doing? Okay. Everybody alive on the other end?
We are here.
Okay.
Yeah, we're just excited to see how this works.
Okay. All right, so let's go ahead. I just wrote a little script here. It's pushed into the repo so that you guys can see it. It's in examples. This is our first example. So we go ahead and we set the degree. Let's set it like to 2, for example, if we want to. Let's do 20 elements. These are all parameters that we can change. Let's set the quadrature rule to be, let's see, p+1, so maybe 3-point rule. And then let's put a 3-point rule on every element by writing a little for loop here in Julia, which Julia makes it really easy. So we're going to put quad rule for every I in 1, 2, lm, n. So that creates an array where there's now for every element it knows to put 3 points on that element. Let's set the CAD domain equal to 1, 2, or 1, 2. And let's set the flex domain equal to 1, like 4. Okay. So we're going to build our basis on the flex domain. So the flex domain is going to carry the basis, but we're going to solve the problem on the CAD domain. Okay, let's put some penalty parameters. So a penalty parameter for the domain outside of the CAD domain, let's set it equal to 1e to the minus 12. So basically we're going to say all the material outside of the CAD domain, we're going to multiply by this parameter, essentially setting it to 0. And then we've got the penalty parameter for the constraint, the displacement constraint is just set that to 1 for now. Usually you set it to be about the same size as Young's modulus, and we're going to assume that those are all 1 as well. Okay, now one really nice thing about the Julia language is the ability to pass around functions. It's kind of a functional programming environment first, which makes it really nice. So if I want to define a load, the way that a really nice way to do it is I can actually define a function called load that takes some parameter x. And let's just say, in this case, the load is 0, right? This would be the distributed load. So we're just going to have it for any x, let's just have it return 0. Okay, so that's one way to create that function. Okay, so now there's a generic function and I can pass that around like an argument, like any other kind of argument to other functions. Let's create a function for attraction, but let's do a different notation. So Julia lets you create simple functions like this as well. This is completely equivalent. So let's set the traction. This is going to be the traction on the right end. Let's just set it to 1. So if you remember, what's the total, like what is the maximum elongation of this bar? If I set the traction equal to 1, the length of this is what? What's the length of this? It's 1, length 1. And remember the formula PL over EA from like way back when you took that class? So P is our traction, so it's 1. The length is 1, and the EA is 1. So the total displacement at the right endpoint should be 1 in this case. So that's what we want to check for. So we set our traction equal to 1. Let's create a function that models our constraint. In this case, it's just going to return 0 because we want the displacement to be 0 on the left endpoint. Okay, great. So now we've got all of our parameters. Any questions on that, what I've done so far? Where it maps into what we've learned?
Could you put a vector in your functions if you wanted to?
Yep, those functions can return anything, any type that you want. So for more sophisticated, like it could be like the load could be like a linear ramp or quadratic or whatever you want. For now, we're just assuming, because I want this very basic linear response, I'm just putting in constants. But that's the beauty of being able to pass functions around, is that they can, any implementation you want can go in the function. It doesn't change anything with regards to how the code operates.
So with your constraint, how are you defining that the constraint only exists at position, I think it is 1 that you have there?
What that
It only
means
goes
is
from
the
1
only,
to
yeah, the only time that that function will be called is for x equal to 0 on the left endpoint. It's just a general function. You could call it for any x and it would always return 0, but in our problem setup, our displacement constraint is being set at, well, what is it? It's at x equal to 1.
Yeah,
It's at the left
okay.
endpoint. Yep. X equal to 1. Okay, so now let's build our spline basis from this information. So I call these layouts, and it's just like a spline basis. And the way that you build it is you need to import. Did I import Coreform IGA? I can't remember, not yet. So you go ahead and import the library, the package. So that will make all the symbols available, all the different routines available to you. And it goes ahead and brings it in. Takes a little bit because it compiles it. Okay, now I can create a spline by saying Coreform IGA dot, and then there's a class, there's a module called basis spline. And inside of that module, there's a routine called build uniform H max K. So it's uniform in H, so it's uniform element sizes, and the smoothness denoted by K is going to be a maximum. So it's, if you have like a degree 2 spline, it's going to be C1 between all of the elements. And it takes the arguments degree, element number, and then we set the domain equal to the flex domain. Because remember that the domain over which the spline basis is built is our flex domain. Okay, so there's our layout, and it goes ahead and prints all the inner data members. I'd encourage you to go and read the code so you can see what all of those are. I've kept it very simple, so it should be very easy to get yourself into it. All right, now let's create some geometries. Let's create some nodes, because that's how we're going to project our basis onto the CAD domain in physical coordinates. So again, there's a routine in here called Coreform IGA dot basis spline dot nodes equally spaced. Okay, and you just give it the layout, and then it will return. See, it goes from 1 to 4 because these are the nodes on the flex domain. So it goes from 1 to 4, and they're all equally spaced nodes. And there's one node per function. All right, so now we're good. Let's just solve our problem. So our problem is going to return a vector of displacements and a Lagrange multiplier. And so let's go ahead and call Coreform IGA dot flex representation method 1D dot solve. And then we're going to pass in the layout, which is our spline basis, the nodes, our quad rules, our penalty parameter on the CAD domain, and all of our kind of problem parameters, EA. Let's pass in the load function, the traction function, the penalty on the displacement, and the constraint function. And then let's let it solve our problem. And then we'll go ahead and plot the solution. Okay. All right, so we solved our problem and it returned what it believes to be the solution. So let's go ahead and set up some plots so we can begin to look at it. So you look at plot, let's import the plots capability. Let's create a plot that we can manipulate. And now let's go ahead and plot the solution over every element. let's just worry, the Lagrange multiplier is a single number. So if you want to know what the Lagrange multiplier was that it returned, there it is, 1, which is exactly right. And in fact, I might have an exercise where you go through and show why that's correct. But so underneath the hood, this is using a very simple Uzawa iteration on the big mixed problem where you've got the different blocks, the K block, B block, and there's some other things in there that I'm going to talk about after I go through this demonstration that make it more robust. But okay, so lambda, that looks right. I know the exact solution for lambda is 1. Because if you think about it, the force that's being, the traction at the end is 1, right? So lambda is defined to be the negative of the, so lambda is defined to be the negative of the stress at the left endpoint. It has to be equal and opposite, right? So the stress better be -1 and lambda is the opposite, which is +1. So this is exactly right. You have balanced forces. So that's what you would expect lambda to be. It's the force required, the stress or the force required to enforce the constraint at where it's being applied, which in this case is x equal to 1. If we want to take a look at the displacement function, let's go ahead and loop through the elements. So for every element, we want to plot our field. So I have a module called field, where you can plot just generic fields. So you pass it the plot, the layout, the nodes, our displacements. So the nodes define x and the displacement defines y. Like it's going to create a graph in the xy plane where x is coming from nodes, because that's how you compute the geometric map. And then d is how you compute the displacement field. And then we compute it, and then you can just pass in whatever kind of a plotting function you want. So I have a function called f, which just plots the values of the field. So this will plot the displacement. You can also pass in derivatives here, so you can look at like the differentials of your solutions and stuff. And then we go ahead and end it. And so, whoop, oh yeah, I put the wrong thing in there. So this needs to be, okay. So now it's done, and we can just type PLT and you'll see the plot pop up here. Okay, so there's our solution. And so there's some interesting things here. So you can see that each element is colored differently. So you can see up here, there's a C1, so the traction is actually being applied right in the middle of this pink element. And this pink element is a quadratic function. So the solution is linear, but notice if you cut the element in half, you don't have any guarantee that you're going to recover that linear perfectly. So there's a little bit of an approximation here that we can now work on, try and improve. But otherwise, boy, we really get a nice linear approximation. So the displacement is 0 at x equal to 1, and then it's a linear function, and the displacement is exactly 1, we're close to 1 at x equal to 2. And then this domain out here is just in our flex domain. It's not part of our problem. Okay. Okay, any questions so far on this?
So if you had ended your element right at that mark, it wouldn't have the slight bounce at that point.
Oh, well, let's just see if we can answer that question. How would we do that? So we want to have, we go back up here to the CAD domain, right? It's 1 to 2, 1 to 4. So it's going to be multiples of 2 where we'll match the boundary exactly, right? So if we did 3 elements, we would get it, right? 1 to 2, 2 to 3, 3 to 4. Should we try that? Just a little 3 element guy. Let's try it. If we do 3 elements, just 3 elements, one of those elements should the breakpoint of the element should be exactly at x equal to 2. Do you guys agree with me on that? as I
Sure.
speak into the abyss. Spend a lot of time speaking into the abyss. Let's see, quad rule is going to be the same. Let's reset up this one. This is the nice thing about having a little language like Julia, because it allows you to experiment. So let's go ahead and rebuild this, because now it's just 3 elements long. Is there anything else we have to change? Don't think so. Same degree, same domains, same physical parameters. We have to redo the layout and the nodes. So let's rerun those routines. And now we should be able to just run it. And then just plot it. What's nice about it is, yeah, it'll just replot it automatically. Okay, so and if we type plot, oh, interesting. So look what it did with just 3 elements. Oh, but I didn't do that right, did I? What happened here? 1. See this element. 1. So can anybody tell me what's going on here? There's 3 elements. Oh, this is great. This is great. Okay, I'll give a sticker. I'll give a gold star to anybody that can tell me what happened here.
So you only have 3 elements across your flex domain, and I think you meant to do 3 elements across the physical domain? Or
No,
do you want to have 3 elements across the whole flex?
I said, oh, look, the total domain here is 3. Yeah, I should be able to cover this with 3 elements. I wanted the boundary of one of these elements to land exactly at x equal to 2. But look what happened. It didn't. Why didn't it, guys? Why? You have 3 elements, but look at this one's small. This one is not very big. These 2 guys on the outsides are big. They're kind of stretched.
You didn't solve for linear parameterization, did you?
Ah. Let's actually look at the parameterization. Let's plot that. Can't we plot that? I think we can. So let's see. Couldn't I just do... So if I wanted to plot the parameterization, I think I could just do something like... So now I want the y-axis to be the nodes also, right? But let's look at the df dxc of that, right? So let's look at the rate of change of the parameterization as you move from left to right. I wonder what that'll look like. I haven't tried this. Maybe it won't. Yeah, okay. So there you can see what's going on. Notice that the slope, you see how if this was a linear parameterization, this would be a constant line, right? The rate of change of the geometry with respect to xc would just be a constant line. But notice what's happening here. That's not the case. The slope changes abruptly as you move from left to right. So that's why this element does not line up exactly with what I wanted here. Okay, so what I need to do is I need to go and write a little routine that's, instead of nodes equally spaced, I need to write a routine that generates the nodes so that the derivative of my parameterization is constant. Then you would know you have a linear parameterization. But it's nice to be able to like see it physically, right? These are the implications. So I can't do that today. I'll be able to do that on Wednesday. So what else can we do to improve the accuracy here? What are the other knobs that we can turn here?
Do more elements rather than fewer?
Yeah, we could do more. So let's try. Let's see.
Maybe try doubling the number of elements, or
Yeah,
to split that pink one in half.
yeah, so let's do, what are we at, 20 now? Let's do 40, see what happens. We have to redo the quad rules, and then redo the layout, and then redo the nodes, and then we're good to go, right? I believe so. Oh, I'm still plotting the, that's the parameterization. Oh, but this is nice. I plotted the parameterization, but now you can see that because there's more elements, you see how this little blip is just at the left, and it'll be at the right endpoint too, but you can't see it, but there's just a little blip at the end. And we'll go into this later as to why this is, but this actually will disrupt time steps. It will disrupt conditioning. So this is actually, it looks innocuous, but it's actually quite significant. So let me fix this now to be, we want the displacement, right? We want just the value. Okay, plot it. I wonder if we'll even be able to see the difference. Oh yeah. See how much more accurate that is though? I mean, I wish I could zoom in. I need to write some utilities to do that, but you can see how it's almost going up exactly to 1 before it, you can see it. Can you guys kind of see that?
Yeah, we can see it.
Okay. So, and notice how as it goes from, one thing that's cool about this method, which leads to some of its nice properties, is that notice how as it transitions from the CAD domain into the flex domain, it does it smoothly. You see how it's a nice smooth transition? What that means is it's not going to disrupt convergence rates. And so you're going to be able to converge to quantities on boundaries at the right rate, which is a big deal for these kinds of methods. So this is C1 quadratic. Anybody, you guys feel like you want to experiment in any other way?
Mike, I'm curious about how your weighting functions are affecting the solution outside of your flex domain. Like it shouldn't be 1 in your flex domain, right?
Can you define weighting function?
Well, aren't you using a fictitious domain and then you weight the reaction down?
Yeah, so that's what you're seeing, is that this is the solution to the fictitious domain.
So why was it in the first case that it essentially stayed 1? Why didn't your weighting function drop it?
Oh, well, it's almost arbitrary at that point. You're like basically at machine precision. So it just kind of pops out. There's not like really a pattern to it. It just kind of, I mean, these variations are like on the order, even though in the solution they look this size, it's being dictated by a very small parameter. So it's basically irrelevant. It doesn't matter what this is.
Yeah, but
smooth.
If you did this, if this was a problem we were trying to understand, we would want to see that our reaction load after 2 is 0. And right now you're showing it as 1.
This is the displacement function.
Oh,
so
okay.
the derivative is going to be a constant. So
can you show the reaction as well?
I can show the derivative. Let's try it. I haven't done it before, but let's give it a shot, right? Because we should be able to come right in here and type, you know, I learned Julia and wrote this whole program since like Wednesday. So I'm not an expert, but okay. So let's see. So that should give, we should be looking at the first derivative of our displacement function with this. And the problem here that I don't like is I need to see, how do I, let me create another plot that's clean this up a little bit. Okay, and then let's do this. Okay, so there's the derivative. That's what the derivative looks like. So, let's see. All right. I don't think this is right because what I need to do here is do df dx, not df dxc. That's why you get the weird scaling. Okay, so I'm not quite ready to look at that yet, Curtis, because I don't have the right derivative there.
Okay.
Well, let's see. Maybe I could. Do you think we could write something though? Let's. If I give it. Yeah. Let's see. F. Layout. Nodes. C. So you guys help me write this. Can we write df dx rather than df dxc? Right, so I'm going to get, so df dxc evaluated at the given xc value should just be equal to core form iga dot field dot df dxc layout nodes exc, right? So now I've got that. And so if I want df dx, I need df dxc, dxc dx. So if I need dx dxc at the same location, so I need dx dxc at that xc location. Well, that is core form iga dot field dot df dxc. This isn't nodes. This will be D, and then this will be the nodes E, C. So that will give me, and then what I should be able to do is return df dxc comma xc times 1 divided by dx dxc. Okay, then I should be able to do this, right, Curtis? So now what I do, what happened? So now when I want to plot not this function, but the function deriv, right? What do you think the chances are this works? If you were a betting person, maybe 1% chance? Give it a shot. Okay, let's take a look. Yeah, it worked. See? This is dx, this is du dx, Curtis. I think that worked. Du dx. Yeah, the double check, but that's I think that's what you would expect, right? The slope should be +1.
Shouldn't the slope go to 0 at 2 though?
Well, not necessarily. I have to look at this more carefully, but yeah, if you were looking at the derivative of your displacement with respect to the parametric coordinate xc, then you get this big jump. But we've reparametrized it where we've taken du dxc and then multiplied it by dxc dx, which cancels out all of this jumping stuff.
All right, but like our slope should go for displacement alone. U should go from 0 at 1 to 1 at 2, and then it should flatline.
No, you don't know anything about what happens after that. That's the fictitious domain. Like there's no,
Well, that's
it's
what
not,
it
it's not,
did.
it's not part of the problem. It is just numerics from that point on. Only the
Okay.
CAD domain, is there any physical intuition, right? Like that's where the physical intuition is. Everything else is just numerics. Okay. Well, that was cool. So I guess the point of this exercise, do you see how fast you can prototype things in Julia? And how much you can, I mean, you just define a new function, pass it in, you get a new plot, you can do all kinds of things here, and I'm just doing it on the fly. So both, I wanted to show you that this package now exists, and I'm going to be dumping all kinds of stuff into this. So for those of you who are like wanting to play around with this, see how it's implemented, you can add to it. It's open source, so you can fork it and do whatever you want with it. But okay, any questions on this?
So just a quick question about, so when we added the elements, or changed the elements from 20 to 40,
Yeah.
would the same thing have happened if we just like increased the quadrature points for each?
Ooh, man, that is such a great question. I can't resist, Kirk. We have to try that. So he's asking about how does quadrature. Okay, so let's set up a little test problem. Okay, so let's do let's go down to like 3 elements. I don't remember what we were at before, but let's do 3 elements. Keep it at degree
So
2.
really quick, could we write this into its own script instead of typing it directly
Oh,
into
yeah.
Julia so we can
Yeah.
have something to reuse and
Yeah,
leverage?
that's what I was doing. I'm referencing a script. That's how I'm remembering what to type. So here's a little script, right? Stretching of an axial rod. You can turn, this is a little script. You can turn it into a function. You can, so you can do it programmatically. Absolutely. So everything that you would expect to be able to do with the scripting language, you can do with this. It's just a module now. It is a package, a Julia package. You install it. It takes care of all the dependencies, and it now plays with anything else you want to do in Julia. Okay, so let's go back to the quadrature issue, right? Because in this example, I am evaluating the traction. Essentially, the CAD domain ends right in the middle of a flex domain. And so that's a weird situation. Like, how am I integrating that exactly, right? Like there's this kind of like discontinuity that's occurring mid-element that should affect the accuracy of things. So let's take a look at what that does and how we can change it. So we'll set the quad rule to, let's start out really low. Okay, let's start out like with 2 points and just see what happens. So that would be like a reduced quadrature rule. Okay, so then we'll do that, and then all right, so we have 2 points per element. Let's recompute our layout. Okay, so here's the layout. And let's recompute our nodes. All right, now let's solve the problem with that, Kirk, and see what the plot looks like. And then we'll start messing, then we'll just we'll just up the quadrature points over and over again and see what happens. All right, so okay, so there we go. There's our problem. Now we want to plot. Let's clear this if I. All right, and then let's just copy this in. All right, and then let's plot this guy. Okay, so there we go. That's 2-point quadrature. Should we just now change? Let's just iterate on the quadrature rule now. Let's go to 3-point. See what it looks like. Nodes shouldn't change. Mhm. Okay, so that's interesting. Let's keep going up in the quadrature rules. Let's jump to like 6, see what happens. Oh, there we go. Look at that. So you can see that at what's happening here is the reality is that Gauss quadrature, I'll draw a little picture here, because this is a very important point. You can see how global the influence of this is if you don't get this right. So what we're doing here is we have this element that goes from here to here. And we're trying to basically apply, so there's no traction, we're applying this function abruptly right here. So there's kind of a, what I would call a soft discontinuity right here. And our physical domain, right, ends here. But we're just applying like standard Gauss, right? So maybe 4 points would put a point here, and then maybe like, does that make any sense at all to do it that way? Like, is this even relevant anymore? If the domain of integration is really this here, and my points are with respect to the flex domain, which is kind of irrelevant, right? Like, do you expect this quadrature scheme to give you an accurate representation of your function? Why or why not?
I would say no, mostly because you just don't have enough points, but also because you have a discontinuity between two different integration points
Yeah,
that are supposed to be in
Yeah.
the same function.
right. So what you would really want to do is either in 1D, you can play all kinds of tricks because it's so simple. What I would do in 1D, and I'll probably implement this, is go ahead and create a composite rule where you know that there's a break, and then put 4 points like this, and then 4 points in here, and then that would work really well. Let's say you didn't exactly know where this continuity was, like in multiple dimensions. Then what you should do is you should implement a subdivision scheme where you keep subdividing the elements down, right, until you get enough points, right? You just kind of over integrate. What we can do now is let's just ramp up. I mean, this doesn't really make sense. And so the basic takeaway here is that we need more sophisticated quadrature. Okay, and we'll get into that later, but you can see that there's funny things going on where you have discontinuities emerging mid-element, and you're just using standard Gauss quadrature, and that assumes that the integrand f is C infinity, is very smooth. So there's no reason to assume that Gauss quadrature is going to do a good job. So let's just do like the next dumbest thing and just ramp up the number of quadrature points. Let's go to like 10, see if that helps at all. It may or may not, right? Because at this point, you're just throwing random points because you have this discontinuity, which means that all of the theory for Gauss quadrature kind of goes out the door. Okay, you see what's happening? Do you see how it's getting better and better? Right? You have this kind of one outlier, and it probably has something to do with the particular distribution of points. But as now at 10, it's kind of getting better and better. So you can see that really a lot of this error is coming from quadrature, not the number of elements. Okay, now let's try as a last little example. Let's do linears where now let's have an element that matches the endpoint. So okay, so what do we want to do now? We want to set the degree equal to 1. How big is the domain? 3 elements. So let's do 3 elements. So if we do 3 elements and the boundaries line up and the solution is a linear, what do you expect? That's kind of a leading question, I guess. What do you expect? Let's just do low quadrature. And,
Just throwing a guess out there, it should be almost exact.
even better, it should be exact because the solution should live, even though you have
Do you have a
elements that-
C0 continuity?
yeah, because it's linear.
Yeah, then it'd be exact.
Okay, so anything else I need to change? Just the layout in the nodes. Okay. Now we can solve our problem. Let's give this one a look. So you can see we nailed it, right? You see how it's a linear? It goes from 0 to 0.75 to 1.25. Yeah, so let's just take a look here. So we've got oh, I need to clear that out just a minute. Yeah, so if there's not a bug, this should be exact. Yeah, and it is. No, it's not. What's going on here?
Somehow it like has some trying to get some sort of curvature in there for some reason.
No, this is, I didn't do something right here because this should be a linear parameterization. What's going on here? Let's see. How many elements are there?
It looks like you need 4 elements. This is a linear parameterization, but you only have 3 elements here.
Is there 4? How big is the CAD domain? Did I just misread that?
Flex is from 1 to 4, right? So you're going to need
3 elements.
well. Okay, go back.
Yeah, that's weird. Why am I ending right here? That's wrong.
Yeah, there's got to be something in
Yeah,
the
it's a bug. It's a bug. I'll fix this so we can explore it more later. It should be. I did this yesterday and it worked anyway. It should go exact a perfect line from 0 to 1, and then but there's some bug, some error. Okay, so for the students that are taking this class, I would suggest that you go to this link and I'll post it. This link right here, and go ahead and follow these directions and start doing the same thing. And then I'm trying to figure out how to integrate it into the class. You guys are the guinea pigs, so I don't have all the answers yet, but I'm getting there. Okay, let's end it there. I'll stick on for a little bit and answer any additional questions, but thanks everybody.
Thank you.
Any other questions for me?
Thank you.
Thank you. Okay, let's see. So my students who are still on, what do you guys think of this little tool?
Pretty cool.
I like it. Yeah.
All right, well, Chris and Kaylin, can you guys hold on? Everybody else
Yeah.
drop? Okay, thanks. Kyle, could you make me the host and then drop?
Yeah. There we go. There we go.
All right, guys. Curious what you guys think of that, going through the material like that. I've never done anything quite so hands-on before.
Yeah, I think one thing that would help, and we've talked about this, but you're going through a lot of these functions, and did you see me? Sorry, just a second. All right, Emma, go ahead. Thank you. That's what I get for leaving my door open. What I was gonna say is, I think it would really help to put these in the Pluto documentation where you can see the math kind of side by side with these functions that you're using. I think what you
How do I stop the recording, by the way? How do I, where is it? Okay, hold on.
it's
There
like
we go.
should be up at the top since